In this short video, I'd like to review some things about partial pressure of oxygen and then also discuss the oxygen hemoglobin dissociation curve. So here's a review slide that we've seen before, and this describes the partial pressure of a gas, and specifically it describes partial pressure of oxygen and the calculation. So to calculate PO2 in room air, it's the percent of oxygen expressed as a fraction, so 0.2093, times the total barometric pressure, the air pressure, which is 760 millimeters of mercury at sea level. That's about correct. So the PO2 in room air is about 159 millimeters of mercury, and that's what we've done before, and that's what we've seen before. So I think I posed a question in notes earlier. What would be the partial pressure of oxygen if we spent the rest of our semester and hiked up Mount Everest? And so to start off with, what would be, these are the two things we need, right? So we need to know the percent of oxygen on Everest, and we need to know the total air pressure on Everest. So first question is, what is the percent of O2, the percent of oxygen on top of Everest? And typically everyone thinks that that percent goes down, and that's not correct. The components of air are the same at Everest as they are down here. It's still the same percentages. So the percent of O2 is still 20.93%. So it's not like the composition of air changes. It's still the same percent of the gases. Yet what does change? What does change is the total air pressure. It's no longer 760, and I had to look this up online. It's estimated to be about 200. So of course, think about this. The air is much less dense. There's less air pushing down on our heads. The air pressure is less when we're up at altitude. So now we can do the simple calculation. So we know the percent of oxygen is the same, so it's 0.2093, but the air is much less dense. So instead of 760, I looked online and it's around 200 millimeters of mercury. So now the partial pressure of oxygen in room air on top of Everest is about 41.8 millimeters of mercury. Compare that down to here of 159. I mean, that's just amazing. And it's amazing that there's some individuals that can hike Everest without the use of additional oxygen, like carrying a tank of oxygen. I don't know if you know this, but SUNY Cortland actually is not quite at sea level. And SUNY Cortland is a little bit higher elevation, I think like 900 feet. I'm not sure exactly. So it's not exactly at sea level. So what would be the PO2 in room air at SUNY Cortland? Is it going to be equal to 159 or above or less than 159? And how are we going to get there? Is the percent of oxygen at Cortland the same as it is in other places? Well, yeah, it's not the composition of the gas is any different. So it's still 0.2093. But the barometric pressure is slightly less. We're a little bit above sea level. So I looked at my barometer, and today we're at 740 millimeters of mercury. So we're a little bit less, 155 millimeters of mercury instead of sea level, which is 159. So some great little applications and review and calculations of partial pressures of oxygen. So these are also some other review notes that I'll go through these, and we've seen these before. But now what I would like to talk about is how oxygen is dropped off at the working muscles. And this is the oxygen hemoglobin or oxyhemoglobin dissociation curve. So it's a curve, it's a graph. And I'll try to explain this graph. Our book has several nice pictures of the graph. There's a nice Khan Academy video that I've asked you to look at that also sort of discusses this oxygen hemoglobin dissociation curve. And I have a couple different versions of the curve. Here's one that I copied from our book, actually. And there's some other ones and some ones I found online. So let's just look at all the parts of this graph. So on the horizontal x-axis, it's the partial pressure of oxygen, just what we calculated out, in millimeters of mercury. And so I think in a previous set of notes and in a previous video, some numbers I asked you to remember. Arterial PO2, so that's the partial pressure of oxygen in the artery, it's about 100. And the partial pressure of oxygen in venous blood at rest is about 40. So those are two good numbers to remember. Great. On this left-hand side y-axis is the percent of hemoglobin that is saturated with O2. So it's a percent. So conveniently, the scale is also from 0 to 100 because it's a percent. And with this graph, we are actually going to start not at the origin, not at 0, 0. We're going to start at the top right of this graph because this is the pathway of oxygen. So let's look at blood leaving the heart or blood leaving the lungs. Let's look and see what it is. So arterial blood is about a PO2 of 100, and it is almost, they've drawn a line for us, it's almost completely saturated. The hemoglobin is almost completely saturated with oxygen. It's about, what is that, 97, 98% saturated. I think of saturation as a sponge. So this sponge is almost full of water. It cannot soak up any more water. Something new on this graph, or relatively new on this graph, and I'm just looking right now, some of the numbers are weird, but is the right-hand side y-axis. And we've actually calculated this out. This is the content of oxygen in blood, the content. So it's milliliters of oxygen in 100 milliliters of blood. And if you remember, we did that. We knew how much hemoglobin someone had times that constant of 1.34. And for males with a typical hemoglobin, the CaO2, the content of oxygen in arterial blood, was about 20. I think that's a value we calculated out, or 20.1 or something like that. And so here on this graph, they say, okay, when oxygen is almost completely bound to hemoglobin, the hemoglobin is almost fully saturated, the arterial blood has a content, a CaO2 of almost 20, and so whatever it is, it's 19 or something, maybe 19.5 on this graph. Great. So that is oxygen in arterial blood. So now let's look at the pathway of oxygen, and let's look at the venous blood at rest. So we're going to follow this graph, and we're sort of going to go down in this direction. And so I told you that a value, and they've put in a yellow dashed line, a value at rest for venous blood is about 40. And so what is that hemoglobin saturation? That's about 75%. So the hemoglobin in the venous blood coming back to the heart is still carrying oxygen, but that's fine. We're at rest. We don't need to drop off everything. What is the venous content of blood carrying oxygen in mils of oxygen per 100 mils of blood? Well, let's just go over to the right-hand side axis, and I don't know, what is that, 15? So now the CVO2, the content for C, oxygen in V, venous blood, is about 15 milliliters of oxygen in 100 mils of blood. So now I'm going to ask you to calculate out the AVO2 difference. That's the content of oxygen in arterial blood minus the content of oxygen in venous blood. And I'm going to use the number 20 because, it's very easy to remember. So it's just 20 minus 15. So the AVO2 difference, the content of oxygen in arterial blood minus the content of oxygen in venous blood, is 5. So 5 mils of oxygen in 100 mils of blood, and that's how much got dropped off at the muscles. But this was a resting condition, so that's fine. Great. So this is this nice graph, and this is another graph I found online, and it's exactly what we've described. There's a little bit more detail in here. And actually what we just described was, unloading of oxygen at the tissues, 20 minus 15. Great. And we described this as arterial blood that is almost 100% saturated and is at about 100 partial pressure of oxygen. And then we followed this graph down to a resting condition. The veins at rest, the PO2 is about 40, and it's maybe, 75% saturated, and the CVO2 is about 15 mils of oxygen and 100 mils of blood. So this is rest. Okay, fine. Well, we, of course, in an exercise physiology class, we are interested in exercise. So we're going to continue on this graph, and we would like the CVO2 to be really low, way down here someplace. And so a typical PO2 in the veins at rest, another good number to remember, is about 20, not 40, but now down to 20. So you can see that we are going to be even lower on this curve. So now maybe we're at a percent saturation of a 20 and maybe a CVO2 of 5. And now the AVO2 difference is this value. It's from 20 down to 5. So that AVO2 difference would be 15, right? 20 minus 15. Yeah. Great. So, but you know what? If I'm at VO2 max, I don't even want 5 mils of oxygen going back to the heart. I don't want the hemoglobin to be 20% saturated. I would like to drop off even more oxygen at the working muscles. So you know that if we are exercising at a high exercise intensity, what happens to temperature, body temperature, or blood temperature? It goes up a little bit. What happens if we're close to VO2 max? We're doing a lot of fast anaerobic glycolysis. We're making a lot of lactic acids, so it's a more acidic pH or a more acidic condition. So the pH will be slightly lower. Let's look at this graph. Here's a normal blood pH of 7.4. A slightly acidic condition is 7.2. So now let's pick on this same PO2 of 20 and notice that the oxygen hemoglobin graph got shifted or moved down to the bottom and to the right. And so now we're actually at a lower part on this curve. So we're dropping off even more oxygen at the working muscles. And the same is to the same is true with temperature. So here on this bottom panel, 38 degrees C is a normal temperature, 43 degrees, we've elevated it. So if we pick a PO2 of 20, this curve has gotten shifted down to the bottom of the graph and over to the right. You also know that at close to VO2 max, we're making a lot of CO2s. We're blowing off CO2s. Here's high CO2s that will also shift this curve over to the bottom and to the right. And this is called the Bohr effect. The Bohr effect is a rightward or downward shift of this graph that favors offloading of oxygen to the tissues. And that's what you would expect. That's what we want to do when we're close to VO2 max. We want to be unloading more oxygen. So here's now my graph. I tried to redraw it. We're now unloading more oxygen at the working muscles. And now this AVO2 difference is 20, and maybe it's all the way down to like 2 or 1 or something. So a nice explanation of the oxygen hemoglobin dissociation curve. Look at some other Khan Academy videos and review the notes in our book.